All right, so thus far, we've looked at objects that are undergoing purely rotational motion, like a ceiling fan or a machine gear turning. We're going to talk about rolling objects now, and that's nothing more than an object that is undergoing both linear motion and rotational motion. We call that rolling motion. And while you may not have thought of it, we interact with rolling motion all of the time. If you've ever ridden a bike or anything with wheels, those wheels are rolling along the ground. Every moment that wheel is touching the ground, it's moving linearly forward through space, but also rotating or rolling. We can relate the linear and rotational motion of that object as follows. If we consider a circle with radius capital R, we know that the circumference of that circle would be equal to 2 pi times r, right? That's something that we're aware of. Now, I want you to think about rolling a circle along the ground, or a bike and a bike wheel riding along the ground. If you were to think about that bike wheel making one full revolution, like in this diagram shown, we would see that as the bike wheel turns, by the time the bike wheel is back to its original position, we've basically unraveled the circle such that the distance that bike wheel has traveled is actually equal to the circumference, 2 pi r. I want you to think about maybe unwrapping this tire. And if we could take the bike tire and just unwrap it so that it became just a flat line, we stretched out that circumference and laid it flat on the ground, we would see that by the time the circle makes one revolution, by the time the wheel comes back to its original position, the bike and the wheels have traveled forward a distance equal to the circumference of the tire. This is the same phenomena that you saw in the rotational motion demonstrators, where every time it made one revolution, it unraveled the string by the circumference of the circle you attached it to. We can use this information to help us connect the linear and rotational motion of the object. We know that delta x here, right, my linear displacement is what I'm talking about, will be equal to 2 pi r. Now, if this wheel makes 2 full revolutions or 2 rotations, what would the delta x be in this case? Right? Well, delta x for 2 rotations would be equal to 4 pi r, right? 2 times the circumference. 3 rotations would be 6 pi r. 4 rotations would be 8 pi r, and so on and so forth. Now, because we've already defined a term called angular displacement that measures the radians of rotation, right? I could say that 1 rotation is 2 pi radians. 2 rotations is 4 pi radians of rotation. And so what I'm starting to see is that delta x, right, my linear displacement, can actually be found just by multiplying, and I'm using capital R here for the radius, that delta x is just nothing more than r multiplied by delta theta. So here, delta theta is going to be either 2 pi or 4 pi or 6 pi. Delta theta is going to tell us how many times the wheel is rotated, and we'll multiply that by r, the radius of the wheel, to find the total linear distance that wheel has traveled. So this equation relates the linear displacement of the wheel as it's moving through space and the angular displacement of the wheel as it's rotating. I'll go ahead and document that in my box on the right. All right, now if I know how much time it took the wheel to travel that distance, right? I can divide both sides by t, and I'll see what happens. If I divide the delta x by t, and I divide this side of the equation by t, well, I know that delta x over t is just my velocity, my linear velocity. And since r is a constant, r, the radius, is not changing, I'm just going to take the delta theta divided by t. And what is delta theta divided by t? Well, that's omega, my angular velocity. And so similarly, the linear velocity of this wheel is also just equal to r times omega, the angular velocity. And lastly, if I take the change in velocity over time, I can derive a similar equation, and you'll see that the linear acceleration ends up being r times the alpha, the angular acceleration of the wheel. We can prove that in the same way. And so just like this, I've managed to relate the linear motion or the translational motion of this bike wheel as it's moving through space and the rotational motion of the bike wheel as it is spinning. If it helps to remember these equations, I like to think about it like the linear term is equal to the radius times the angular term. The radius and the angular term go together on the right-hand side of the equation, and the linear term is on the left side of the equation. Now, these equations are not on your AP Physics 1 equation sheet, so you will need to be comfortable converting between linear motion quantities and angular motion quantities. But remember, this only applies to objects that are rolling, objects that have both linear and angular motion, okay? So these three equations will help you determine if you don't have, for example, delta x, but you have delta theta and the radius, you can get delta x, v, and a using any of my angular quantities. And so these will be what we call our bridge equations, if you will. They bridge rotational and linear or translational motion together and allow you to solve problems that you wouldn't be able to solve otherwise. So please take special note of these equations and apply them whenever you have a situation dealing with rolling motion.